Hey, welcome back to Fat Mama Physics. In this video, we're going to continue on with electron diffraction experiments. And now that we are able to show that an electron will diffract very similar to a wave at a particular sample or a slit or multi-slits, etc., we can then be able to use that to help us measure other properties, such as, say, the size of a nucleus, which Rutherford was unable to do, or he was able to get very close, but he encountered a problem with the strong nuclear force. When an alpha particle gets too close to the nucleus, the experiment will start to deviate from his expectations, which then make it difficult for him to actually detect the actual size of the nucleus, because of the interaction of the alpha particle with the nucleus. But an electron will not be affected by a strong nuclear force because it will be moving too fast. It'll be too difficult for the nucleus to absorb it or to change it or to interact with it as such. So an electron is very nice. It will what would happen is that you have high energy electrons. Their incidence, say, on a gold nucleus, for example, it will diffract around it such as a wave would, modeling the matter-wave duality principle, in which the diffraction pattern is going to look very much like a single slit diffraction pattern. So what that looks like is it has a really broad band in the middle, and then you have a next maxima coming up a little bit later. So hopefully you've seen a single slit diffraction pattern before, and the relationship that shows models this is this one over here. Sine theta is roughly the wavelength of light used divided by b, which is the size of the slit. So say for a gold particle, for gold nucleus with a certain size d, we can kind of model that with this being b. Okay, instead of diffracting at a slit, it's kind of a diffracting around an obstacle. We're going to expect very similar patterns. Okay, so here we have B, which is the size of the nucleus, and roughly the wavelength of light, which is just the wavelength, or the wavelength equivalent, the Broglie wavelength of an electron in our case, and the theta here is the separation from the central maxima onto the next minima. Okay, so notice that to get the whole band, the entire central maxima, this is essentially 2 times the angle that you see there. Okay, so notice that the angle subtends to the next minima, not the next maxima. Okay, so that is just what this relationship is. We are going to use this relationship to help us detect the size of a gold nucleus, given that we know the wavelength of the Broglie wavelength of our electron. So let's take a look at an example. So in this example, in a neutron diffraction experiment, a beam of neutrons, not electrons, of energy 85 mega electron volts are incident on a foil made of lead and diffracted. So this tells us the energy of these neutrons. So hopefully these are going to be the energy. So this is the kinetic energy here. And the first diffraction minimum observed at an angle of 13 degrees relative to the central position where most of the neutrons are observed. So this is the diffraction minimum. So that's exactly there. So that's the correct angle we should use, which is theta equals to 13. From this information, estimate the radius of the lead nucleus. Okay. So this B here is going to be, looks like the diameter of the gold nucleus. So if we want to find a radius, we have to take this and we have to divide by 2 at the end to give us the radius. Okay, so let's begin. And since we need eventually to find this B, which is going to represent the size of our gold nucleus before we divide by 2 to get the radius, this is going to need our wavelength as well as the sine theta, which we have from the question, and the wavelength, we can find the de Broglie wavelength of this beam of neutrons with accelerated at a certain speed. So using the fact that the de Broglie's hypothesis is h over p, in which p is the momentum we know is, if we rearrange for kinetic energy, we're going to get 2 ek, and then taking the square root of that. Okay, so I'm going to reuse that instead. I'm going to use that, substitute it into the wavelength, in which we're going to get the de Broglie wavelength of these neutrons as h over the square root of 2 mass of the neutrons times its kinetic energy. So substituting all that in, we're going to get the Planck's constant over the square root of 2 times the mass of the neutron that's in your data booklet times 85, and don't forget it's mega electron volts times 10 to the power of 6, and then the elementary charge. So this wavelength is going to give us 3.1 ... times 10 to the power of negative 15 meters. So this wavelength then I am going to use in here, in which I'll use in black so we can see this is the next step here. This is going to be 3.1 ... I'm going to save everything in my calculator over sine of 13. And this is going to give us 1.38 ... times 10 to the power of negative 14 meters. And don't forget, that's the entire diameter of the gold nucleus. So to get the radius, we got to divide this one by 2, which is going to give us 6.9 times 10 to the power of negative 15 meters, which is, I guess, roughly 7 times 10 to the power of negative 15 meters over there. Okay, so notice that with this new finding, we are able to take advantage of it to find the size of a nucleus. So there we go. That's electron diffraction experiments for you, from the de Broglie, presented to you by de Broglie's hypothesis. De Broglie. All right, there we go. I thank you for watching. Hopefully you learned something from this video. Good luck. And Fat Mama Physics signing out.